All right, we're recording now. Welcome, everyone. So does anyone have any questions that they'd like on the record before we begin with the lecture?
I have a question about representability, but I guess that can
No, go
wait.
ahead, Arvin. That's great.
It's sort of if you have a sheaf that's representable after a base change,
Mm-hmm.
or let's even say an étale base change,
Mm-hmm.
then does that mean it's representable already?
Let me think about that for a second. So the answer is no in general. And the reason is that descent for schemes is not in general effective.
Okay, so it
So,
is a
so
question of descent then.
yeah, exactly right. So the issue, what will be the case is that it will be representable by an algebraic space. But yeah, that's what happens. So we'll discuss some representability issues actually in a little bit, so that might also answer some of your questions along those lines.
Cool.
Any other questions before we begin? All right, if not, let's get started. So first of all, I wanted to make a remark. So I think Ben Church pointed this out to me in office hours. So what I've been calling a torsor, so let me remind you. So what I've been calling a torsor, so that was a sheaf with some action. Calling a torsor. So that was remember, that was a sheaf with some action by a sheaf of groups such that some condition is satisfied, which I told you was the analog of acting simply transitively on fibers. So some sources call this a pseudo-torsor. So in particular, the Stacks project calls this a pseudo-torsor. Okay, and then what I've been calling a locally trivial torsor, so some sources call a torsor. So this might be a bit confusing. So I'm using this notation because I think people often kind of elide the representability issues and so on underlying like when is a torsor representable, like in Arvin's question, where exactly is it locally trivial, and this sort of thing. And so I'm trying to always say that when I discuss torsors. But if you're ever confused about that, please ask. And I figured I should mention this in case you decide to look at other sources. So in particular, the Stacks project has some very good information on this stuff, and you should take a look, but just be aware that it's using slightly different notation. All right, so with that, I wanna return to where we were at the end of last time. So let me just remind you, we were proving a theorem, which I called Hilbert's theorem 90. And I'll explain why I'm calling it that, because you probably may or may not have seen something called Hilbert 90 in the past, and it might not look exactly like this version of Hilbert 90. But I want to start by recalling the statement and spending a little bit more time on the proof, because we kind of zoomed through it at the end of last time. So the statement was, well, you can look at locally trivial torsors for the group GLN on the Zariski side of a scheme X. There's a map from this, or map to this rather, from locally trivial torsors for GLN on the étale side of X. And there's a map to this from locally trivial torsors on the FPPF, on the small FPPF side of X for GLN. Okay, and the theorem is that all of these maps are isomorphisms. Okay, so let's just remind ourselves what the proof was. So can anyone help me talk through it? So we did discuss it a little bit at the end of last time, but I want to discuss it again now. So the observation was that, so let's let tau be one of these sites. So let's let tau be either X Zariski, X étale, or XFPPF. And we observed that the data of a GLN torsor split by some cover, some tau cover, maybe I'll say, u to x is the same as descent data for a vector bundle relative to u over x. So can anyone remind me why this is true? Any thoughts?
Vector bundles have an associated frame bundle.
Yeah, so one way of saying it was that to go from a vector bundle to a GLN torsor, there's an equivalence between vector bundles and GLN torsors given by sending a vector bundle to its associated frame bundle. But can anyone just tell me explicitly how to actually get out descent data? Anyone remind me of this?
Well, I guess if you have a local trivialization, then on the overlaps, you get an explicit element of GLN. That's the isomorphism of the OM.
Yeah, exactly right. So let's draw the diagram. So we have u cross u over x goes to u in two different ways. So this is, let me draw it this way. So this is what I'll call pi 1 and pi 2. And then we have x here. Let's call this pi. So we have, what does it mean that u trivializes our torsor? It means that pi star of our torsor t is isomorphic to pi star of g as a g torsor, where here just g acts on, as a pi star g torsor, I guess. So g acts on itself by left multiplication. So what that means is that, well, now we're pulling back. We can pull back in two different ways. So we can pull back pi 1 star of pi star t. And because this is something pulled back from x, this is the same as pi 2 star of pi star t. Well, now this is the same as pi 1 star of pi star g, just because pi star t was the same as pi star g. And this is the same as pi 2 star of pi star g for the same reason. Okay, and then the claim is that, well, this arrow here is precisely descent data for t. And the claim here is that this arrow, so what is this arrow? This is, well, it's an isomorphism from g to itself, right? Both of these things are isomorphic to g restricted to u cross u. Okay, and the claim is that an automorphism of such a thing as a g torsor is a section to g. Okay, so what do you have if you have a section to GLN, so an invertible matrix, on double intersections in a cover? That's precisely descent data for a vector bundle. Does anyone disagree with that or have questions about it? So if you have, in other words, if you have on double intersections, if you have a section of GLN, which satisfies the Kosa condition, that's descent data for a vector bundle.
Hey, Daniel, just sorry, a non-math request. Could you possibly switch to a thinner brush size? Because I think it's a little difficult to
sure.
tell between the...
How's this? Is that better?
Yeah, thanks.
Great. Yeah, thank you for requesting that. Okay. So we have a section to G. So we've claimed that for any of these sites, a locally trivial GLN torsor is the same as a vector bundle, or same as descent data for a vector bundle. And now remember, so FPPF descent, which we proved a few weeks ago, tells us that descent data for vector bundles is effective. So what that tells us is that if we have in particular, if we have a GLN torsor in the FPPF site, which is a GLN torsor which is locally trivial in the FPPF site, then it's also locally trivial in the Zariski site and hence in the Etale site, right? So this tells us how to go back and forth. We've now finished the proof. So we have a map here. So what have we done? We've shown, in other words, that for all of these sites, so in other words, H1 of x tau for any of these sites, GLN is in bijection with the category of n-dimensional, in bijection, sorry, with the set of isomorphism classes of n-dimensional vector bundles on X. All right. Are there any questions about that? So that's the end of the proof. So if you have three things and they're all isomorphic to the same thing, they're all isomorphic. Any questions about that? Okay, so here's a fun, sorry, my screen keeps shifting like this. It's doing it automatically for some reason. So here's an exercise. So can you find some other groups, find other groups, like other than GLN, for which Hilbert 90 is true? Is true, or for which it's not true. And we'll discuss a sort of very famous example of a group where it's not true later on in the day. But it's sort of fun. So there are other examples besides GLN where a sort of analogous statement is true, where FPPF G-torsors are the same as for example, Zariski G-torsors. In general, that's not the case. All right. So let me just make a few remarks about representability and local triviality. So first of all, so what did we use here? So we used that descent is effective for vector bundles. So first of all, so suppose G is an affine flat X scheme, or X group scheme, sorry. So here's a question you can ask. So are all G torsors representable by G scheme? Okay, and it turns out the answer is yes in this case. So using affineness. Okay, and we more or less gave the proof last time. So last time I explained how to do this for affine étale group schemes, and the same proof works.
Do you mean by an X scheme? Or?
But yeah, by an X scheme. Sorry about that. So this is by the same proof as last time. So you should try working out the details. So the point is that you can trivialize such a G-torsor by yeah, you can trivialize such a thing flat locally, and then use FPPF descent. Okay, and then the second question you can ask is suppose so given a G-torsor T, and let's suppose it's FPPF locally trivial. You can ask, is it étale locally trivial? Okay, and the answer in general is no. But it's yes if G is smooth. So can anyone give me an example of a non-smooth group scheme? Any thoughts?
Maybe the kernel of Frobenius or something?
Yeah, so if, for example, if you take the kernel of Frobenius on the affine line, are GA. So that's called alpha P, and that's not a smooth group scheme. Another example is mu P in characteristic P. So the thing that represents Pth roots of unity. So that's the, if you'd like, the kernel of Frobenius on GM. Yeah, and in general, in fact, if you take any positive dimensional affine group scheme, the kernel of Frobenius will not be smooth. So that's a great example. Okay, and you could also take, for example, take mu P times GLN, and that's another example. So in general, you need smoothness, and the reason why is that you can just take an FPPF local trivialization. You can trivialize by T itself, and then slice it to get an étale trivialization. So this is a fun little exercise to try, and it's not trivial. But I won't discuss it unless we need it later, and I think we'll be able to avoid it.
Sorry, what do you mean by slice it?
Yeah. So let me say a word about the proof. So proof sketch. So we have T to X. This is our torsor, and we can base change it to itself. Okay, and just a reminder, so this torsor over T is trivial. And there are a few ways to see it. One is that it has a section given by the diagonal map, right? But another is that, well, what was the definition of a torsor? It was that T times T is isomorphic to T times G, the action map. And it turns out that's the same as this triviality statement, right? And now the claim is that, okay, well, this map, this trivializing map, T to X, here, we can this is a smooth map because G itself was smooth, and the fibers of T are isomorphic to the fibers of G, right? So this is smooth. And the claim is that we can find some U in here, closed, so that this composition is an étale cover. So what I mean by slice is slice it to find such a U. And you can do this, for example, using the structure theorem for smooth morphisms. Does that answer your question, Arvind, or do you want me to say more?
You mean like, okay, I guess I just have to think about why such a U should exist, okay.
Yeah, so it's not so obvious, but so imagine, for example, that T was just affine space over X. So that would be like spec of OX, the relative spec of OX adjoining like X1, X2, X3 or something. So how would you find such a U there? You would just set X1 and X2 to 0. So that's slicing, right? Or sorry, X1, X2, and X3 to 0, for example. So that's what I mean by slicing.
Okay, thanks.
Yeah, and in fact, the proof is just do that étale locally, basically, which is something you can do using the structure theorem. Okay, but yeah, I just wanted to mention that for culture. Okay, so let's talk about this theorem here. So let me maybe copy and paste it. I'm sorry. So let's talk about what this means. So let's do some examples. So the easiest example is where X is spec K. Let's suppose N is 1. So we're looking at the étale cohomology of a field with coefficients in Gm, right? So in this case, can anyone tell me what is H1 of spec K Zariski with coefficients in Gm? So I'm asking about line bundles on spec of a field.
Should be 0.
Yeah, it's 0, right? It's because line bundles on a point are all trivial. Okay, and what this is saying is that this is the same as H1 of spec K étale with coefficients in Gm, for example. And this is the same, if you know about Galois cohomology, as H1 of the Galois group with coefficients in K bar cross by the isomorphism between étale cohomology of fields and Galois cohomology we discussed a couple class periods ago. Okay, and this equality between Galois cohomology of K bar cross and 0 is what's usually called Hilbert 90. So this is some kind of massive generalization to any scheme. So hopefully that explains the etymology a little bit. And by the way, there was a question last time about why it's called Hilbert 90, and the reason is indeed that Hilbert numbered his theorems in at least one of his books. Cool. All right, so let's generalize this observation. So example. So suppose now X is any scheme, and n is 1. So what have we computed? We've now computed H1 of X étale with coefficients in GM, namely the sheaf which associates to an open of X étale, an étale morphism to U, the set of invertible functions on U. So can anyone tell me, what is this H1 that we've computed?
Pick.
I'm sorry?
Just pick.
Yeah, it's pick of X. That's exactly right. So this is something we know well. Great. So now we can start computing things. So this is sort of the big accomplishment that we've managed in the last class period. We now know H1 of one interesting sheaf, and we're going to leverage that as hard as we can. Okay, so let's use this. Sorry. So let's compute H1 of X étale with coefficients in the sheaf mu L, where here L is a prime, or L is a number which is invertible on X. So when I say that, I mean, for example, if we're a field of characteristic prime to L, or if you'd like, I mean, we don't need that. We just need L. L is a function on X, and I want that function to be invertible. All right. So can anyone tell me how do I compute this? So I want to use what we've done in the previous example, namely that we've computed the Etale cohomology of GM.
So it's an exact sequence.
I'm sorry?
All right, there's an exact sequence mu L to GM by multiplication by
yeah, exactly right. So we're going to use the following exact sequence of Etale sheaves. So well, I guess it should be 1 to mu L to GM to 1. And this was the map Z goes to Z to the L. Okay, and this sequence has a name. It's called the Kummer sequence. And we talked a few class periods ago about why. Sorry, I'm going to switch back to vertical because this is ridiculous how my screen keeps moving. All right, so maybe that's better. So we talked a few class periods ago about why this is an exact sequence of sheaves in the Etale topology. So can anyone remind me why?
Because after an étale base change, everything is in Lth power.
That's exactly right. So you can just adjoin an Lth power of any given function, and that's an étale, that gives you an étale cover. Okay, so what does this give us? So this gives us a long exact sequence in cohomology, right? If we have a short exact sequence of sheaves, we get a long exact sequence in cohomology. And what does that cohomology look like? What does that sequence look like? So we get 0, H0 of X étale with mu L coefficients. That goes to H0 of X étale with GM coefficients. That's something we know. That's just invertible functions on X. GM coefficients. So this is just taking things to the Lth power. So then we get H1 of X étale with mu L coefficients. So this is what we're trying to compute. And that maps to now something we understand. It maps to pick X. So we've just identified H1 of X étale with GM coefficients as pick X. And now we get multiplication by L here, and we get pick X. And then we get some H2s, and so far we don't know anything about those H2s. And then so on. Great. So this is what we can say about h1 of x étale with mu L coefficients. So for example, let's suppose that now let's make some assumptions on x. So suppose x is proper, and well, let's just suppose h0 of xox is just the ground field k, and suppose that's algebraically closed. So then we can figure out, first of all, that h0 x étale mu L is what? Anyone?
It's going to be 0, right?
Will it be 0? So it'll be the Lth roots of unity, right? So it's the kernel of this Lth power map from h0 of gm.
Yeah. Sorry, yeah.
So it's just mu L of k. Great. And what about h1 with mu L coefficients? Well, so now this map is surjective, right? Because this is just, so what are these groups? So this is k cross in this situation, this is k cross, and we're over an algebraically closed field. So every element of k has an Lth root. So this map is surjective, right? So that tells us that the thing we're interested in, this group, is just the kernel of this map. So in other words, it's pick x, and then the L torsion. Great.
Can I ask a quick question?
Yeah, go ahead.
So we can interpret the pick x here as GM torsors, right?
That's right, yeah.
And so how do we understand the group operation on the in terms of
at the level of GM torsors, you mean?
Yeah.
Yeah, so at the level of line bundles, it's just tensor product, right?
Right.
If you want to think about it in terms of GM torsors, probably the easiest thing to say is you would write down the Čech cocycle describing the GM torsor. So that's some invertible functions on double intersections of some cover, right? On U cross U, where U is some cover. And then you can just multiply those functions together.
Awesome, thanks.
Yeah, great. Cool. So this, I mean, you can also make a geometric description directly in terms of torsors if you'd like, but maybe let's save that for office hours if you're interested. Okay, so this is we've now computed this. So I'll come back to this in a second, and we'll make this totally explicit for curves. But I wanna talk a little bit more about some other examples. So let's try the following. So let's try h1 étale with h1 of x étale with coefficients in the constant sheaf z mod lz. And again, let's assume x is over a field k, which is algebraically closed. So can anyone tell me what this is? And here I want L invertible in k. So we already did this if L is the characteristic of k. So can anyone tell me what this is? So what does the sheaf Z mod LZ look like in this situation? So my claim is that the sheaf Z mod LZ is just isomorphic to mu L if you're over in fact, if you're over a field which contains all the Lth roots of unity. So why is that?
Because you can just define the isomorphism.
Yeah, so how would you do that?
Pick a generator and send one to the generator.
Great. So you have to pick an Lth root of unity, a primitive Lth root of unity, and then you send one to that primitive Lth root of unity. So here this isomorphism depends on a choice of primitive L root of unity. Okay, and let's just be totally explicit. So what is this? This is represented by maps into spec k adjoint t modulo like t times t minus 1 all the way up to t minus l, right? Sorry, t minus l plus 1. For example, and then you have to write down a funny operation on that. And this one is represented by spec of k adjoint t mod t to the l minus 1, right? So both of these things are just schemes of dimension 0. They're disjoint unions of points, using that L is invertible in the base. I'm just using like the Chinese remainder theorem. So one can just by hand write down an isomorphism between those two schemes, just sending points to different points, and hence between the functors they represent. Okay, so what that tells us is that in this situation, so the corollary is that if UL is contained in K, so K has all roots of unity, H1 or Hi in fact of X étale with Z mod LZ coefficients is isomorphic to Hi of X étale with mu L coefficients. Okay, and again, this isomorphism depends on a choice of primitive L of unity. So in particular, once we talk about Galois actions on Etale cohomology, this will not be Galois invariant, will not be Galois equivariant. You can already see that for H0. I mean, Galois acts trivially on Z mod LZ, but not on L roots of unity. All right, cool. Are there any questions about that?
I guess there's a question on the chat window.
Oh, let me take a look. Ben Church says, if I have a non-integral scheme over X, can't I get more elements in mu L? So remember, L is invertible in the ground field. So the answer is no. If L was not invertible, then you could. But maybe could you say a bit more, Ben? Oh, you're with me? Yeah. So in particular, I mean, this is the proof. You just write down an isomorphism between the two representing objects.
I'm sorry, thinking about that for a moment. The Z mod LZ, I mean, if you take an open affine, then the sections are just choosing an element for each connected component.
That's right.
And then mu L also, that means that the coordinate ring on that open affine will have that many factors in the product decomposition. Right?
Yeah, that's exactly right. So both of them will just be mu L to the number of connected components or Z mod L to the number of connected components. Yeah, great. Cool. Okay, so finally, I do want to discuss kind of a geometric interpretation of these things. So we've now computed, so let's suppose X is an affine scheme now. Yeah, let's suppose X is an affine scheme. Just for concreteness, we've now computed H1 of X étale FP, where here let's suppose I'm over a field K, where here P is the characteristic of K. And so let me remind you, this was the co-kernel of OX to OX via the map X to the P minus X, right? So this was this Arden-Schreier business. And we've also computed H1 of X étale Z mod LZ, at least in terms of this long exact sequence. And this is if K is K bar. Great. So these groups have meanings, right? These are on the top we have FP torsors, and the bottom we have Z mod LZ torsors. Right. So in other words, that means something geometrically. That's those are covering spaces with Galois group FP or Z mod LZ, right? So can anyone tell me, like, how would you explicitly write down those covering spaces? So let's say, so here's the question. How does one explicitly write down these torsors? So for example, suppose I'm given y, which I'll write in square brackets to indicate that I'm thinking of it as like the torsor associated to some geometric object. So suppose I'm given something in H1 x étale FP, which I told you is the co-kernel of some map from OX to OX. So how do you actually write down this covering space? Any thoughts?
Is LP in this example?
Yeah, this is, sorry, maybe it's not so clear what I wrote here. It's supposed to be a P. And here again, P is the characteristic. Oh no. Any thoughts? So let's represent an element in this H1 via just an element of O, right? We said this H1 is some quotient of the functions on X. Yeah, so Arvin says Arden Schreier. Yeah, exactly. So here Y is cut out by, let's say Y to the P minus Y equals A, where here A is some element of OX, which we're viewing as giving us an element in H1FP. So this is called an Arden Schreier covering. Okay. What about, let's try the situation with L. So suppose L is not equal to the characteristic of K. And suppose I'm given Z, which is in H1 of X étale, let's say mu L. And let me assume for simplicity that pick X is trivial. So in that case, I can write this as OX as the co-kernel of OX cross to OX cross, where this map is X goes to X to the L. So can anyone help me write down Z? What is this mu L torsor I get?
So it's going to be Z to the L is equal to?
Yeah, exactly right. So it's Z to the L equals F, where here F is the element in OX cross, an element in OX cross, sorry, representing our class in cohomology. Okay, and how does mu L act on it? It just acts by multiplication on Z. Okay, so I do want to remark, I mean, this story of kind of explicitly writing down covers has a name. So this is called, well, this is the very beginning, I guess, of what I would call explicit class field theory. Explicit geometric class field theory. Which gives you a recipe for writing down abelian covers of curves. And I mean, I've only discussed this very special situation where the Picard group is 0. In general, the Picard group intervenes in a kind of crucial way, and we can talk about that some other time if you'd like. But that's all I want to say for now. All right. Are there any questions about that before we start computing the cohomology of curves, or about anything else? All right, if not, let's take a 1 minute break. I'm gonna get myself a glass of water. And then when I come back, we'll start computing the cohomology of curves. All right, everyone, I'm back. Any questions have arose while I was getting water? All right, if not, let's start with computing the cohomology of curves. So this is like my favorite topic in this whole course. And we've already kind of started doing the computations. So let me kind of tell you what the goal is, and then what we've proved so far and what we've left to prove. So the goal is the following theorem. So suppose X is a smooth curve over a field K, which is algebraically closed. Then the following theorem is true. So then HI of X étale with cohomology in GM. So this is somehow the sheaf that we can actually compute with, and everything else will come from that, is the following. So we already know what H0 is. It's just global sections of GM, which is invertible functions on X. We've just finished computing H1. Can anyone remind me what it was?
Pick X.
Yeah, it's pick X. Okay, and then the hard part, so we've done 1 and 2. So the hard part is that it's 0 if I is bigger than 1. So we've done this, and then this part is hard. All right. And the corollary is probably what you would really think of when you think about the cohomology of curves. So it's the following. So X is a smooth proper curve now, and connected over an algebraically closed field, and L is a prime not equal to the characteristic of K. Then we can compute the cohomology of X with coefficients in the constant sheaf Z mod L to the NZ. So this is what I told you it was meant by étale cohomology earlier in the course. And what do we get? Well, we know the answer is if I is 0, we just get the global sections, which are Z mod L to the NZ, if I equals 0. So we've more or less computed the answer if I is 1. So what we said it was that it was pick of X. Well, we did the case where N is 1, but in general, we just get L to the N torsion here. And this we can write explicitly as Z mod L to the NZ to the 2G. This is I is 1. Then we'll get Z mod LZ for I is 2, and unfortunately I didn't make my brace long enough here, and we get 0 if I is bigger than 2. Okay, so this is the corollary. So can anyone explain to me how to deduce the corollary, assuming the theorem?
What is written next to proper?
Sorry, connected.
Thank you.
So can anyone tell me how to prove the theorem? And we're going to have to use a black box here, unfortunately. So if you haven't seen a little bit about the theory of abelian varieties, then I'm sorry, I'll be explicit about what the black box is, but we're not going to prove it. So can anyone tell me what pick of a curve looks like?
Yes, Jacobian.
Yeah, so it starts with the Jacobian. So the Jacobian is the connected component of the identity in pick. So this is pick 0 of x. So that maps to pick of x. And what's the co-kernel?
A neuron Safari group.
Yeah, so in the case of a curve, that's z, right? So this is just the degree map. So this is something, if it's not familiar to you, you should look at Hartshorne chapter 4 or somewhere else, which discusses the cohomology of curves. Okay, and then the black box, which this isn't a course on abelian varieties, which I'm going to use, is that this Jacobian of x is a g-dimensional abelian variety, and in particular, its L to the n torsion is, as an abstract group, isomorphic to z mod L to the nz to the 2g. So if you're familiar with the elliptic curves are one-dimensional abelian varieties, and their L to the n torsion looks like z mod L to the nz squared, and this is a higher dimensional generalization of that. Okay, so can anyone tell me how to use this to prove the corollary?
Does that statement require algebraically closed?
Yes, but here we're assuming algebraically closed in both of these theorems.
Okay, I just want to make sure.
Yeah. So I mean, yeah. This is a geometric statement. I mean, in general, the Jacobian could just have one point, namely the identity. One rational point, rather. Yeah. Okay. So let's do it. So the Kummer sequence. So that was this short exact sequence of sheaves, which went 1 to mu L to the n to GM to 1 gives a Longzap sequence, and let me show you the relevant part. So it gives us 0 to H1 x étale. Well, we can say z mod LZ, because this is z mod L to the nz, sorry. Because we're over an algebraically closed field, this is isomorphic to the constant sheaf z mod L to the nz to H1 x étale, sorry, to H1 of GM, which we said was pick. This goes to pick. This is multiplication by L. This goes to H2 x étale z mod L to the nz. Okay, and then the rest of the sequence is 0 by the theorem here. So by this fact that the Etale cohomology of GM vanishes in degree bigger than 1. Okay, so what we're doing is we're computing the kernel and co-kernel of this this map on pick. So we need one more fact, which is that the k-bar points of x is a divisible group. Okay, so what do we get? Here we get that this is pick x L to the n torsion. And well, pick x is an extension of z by an abelian variety, and z has no torsion. So this is the same as the Jacobian of x, L to the n torsion. And this, I told you from our black box, was z mod L to the nz to the 2G. Maybe I should have said this is a curve of genus G. All right, so that proves I is 1. And now to get I is 2, we need to compute this H2, right? So what do we get here? So this is the co-kernel of pic X to pic X, where this is multiplication by L to the N. And what is this? Well, because the Jacobian is divisible, this is the co-kernel just of Z to Z, where your multiplication by L to the N. And that is, as desired, Z mod L to the N Z. Okay, and then the vanishing in higher cohomology just follows again from this vanishing of the higher cohomology of GM. So that modulo this black box, namely the structure of abelian varieties, is a proof of the corollary, assuming this goal theorem. Are there other questions about that?
Again, just scroll down for a moment.
So all I did is I wrote down this 4-term exact sequence, which just came from the Kummer sequence. I said that this H1 is the kernel of multiplication by, it should be L to the N on pic. And H2 is the co-kernel. And then the structure of abelian varieties, namely these two black box facts, that the torsion is Z mod L to the N Z to the 2G and the identity component is divisible, let us compute the co-kernel and kernel.
I'm confused. If pic X is divisible, then wouldn't the co-kernel...
Pic 0 of X is divisible. Right, this Z part is not divisible.
Oh, I see.
Yeah, so the Jacobian is divisible is the point. So yeah, so what is that saying? It's saying that, well, what you should do if you really want to write this out is write out the snake lemma for multiplication by L on this short exact sequence. So what this is saying is that the co-kernel of multiplication by L on the Jacobian is 0, which means that the co-kernel on pic is the same as the co-kernel on Z. So maybe I'll write this as an exercise. So check this using the snake lemma. While using the black box and the snake lemma. So what I'm suggesting is applying the snake lemma to what you get by applying multiplication by L to this short exact sequence. And Freddie said, so that should be L to the N in the, yes, yeah, sorry, this should be L to the N, not an L, sorry about that. Great. Okay, and again, I just want to remark, so these isomorphisms, once we discuss Galois actions, are not going to be Galois equivariant. Yeah, I guess, I mean, I can say what I mean by the Galois action briefly. So X is a scheme over K bar. If it started over some subfield, then the Galois group of that subfield acts on this scheme. And these are functors. So the Galois group acts on the functors themselves. So in general, what I'm saying is we have these isomorphisms. H1 is canonically, well, after choosing a root of unity, so for example, if K contains the roots of unity, H1 is canonically this. It's more canonically this if we put a mu L instead of a Z mod, mu L to the N rather than Z mod L to the N Z. But this isomorphism won't be canonical. And moreover, here this, in fact, what will happen, and we could prove this now, but I won't do it now, I'll do it later. This Z mod L to the NZ is really the action, the Galois action will be via the cyclotonic character. All right. Are there any questions before I, so maybe the remark is, yeah, so I said these isomorphisms are not Galois equivariant. So are there any questions before I move on to discussing what goes into the proof? Okay, so let me just remind you what we're trying to do now is we're trying to prove this goal theorem, which computes the Etale homology of GM on a smooth curve over an algebraically closed field. So we've already computed H0 and H1, and now what we want to show is that HI of X Etale GM is 0 for I bigger than 1. So let me actually rewrite that as our goal, and then I'll discuss the ingredients. So the goal now is to show that HI of X Etale GM equals 0 for I bigger than 1. And here, X is a smooth curve over an algebraically closed field. Okay, and this will have the proof will have 3 ingredients. And from least formal from most formal to least formal, they are, first of all, we'll need to understand the Leray spectral sequence. Which will also be useful throughout the course, so this is a good opportunity to introduce it. So 2, we'll need to understand the so-called divisor exact sequence, which I think will be familiar from the complex analytic world. And 3, we'll need to understand Brauer groups. So these are, it's really one of my favorite topics, and I can't wait. So I want to start with the Leray special sequence, but before I do that, are there any questions? I mean, I'm not giving you the plan of the proof yet. I'm just kind of giving you the ingredients, and so we'll develop these ingredients, which are interesting in their own right, and then we'll come back to the statement. So hopefully, I think probably we won't have time to talk about more than the Leray special sequence today, but we'll see. So are there any questions about this before I dive into these ingredients that we're going to need for this computation? All right. So let's start. So we're now starting a new subsection, I guess, which I'll call push forwards and the Leray spectral sequence. So let me just remind you, first of all, what a push forward is. So suppose I have f x to y, a morphism of schemes. Then we get a map, a functor, f lower star, from sheaves on x étale to sheaves on y étale. Can anyone remind me how this functor is defined? So what do I need to do? So here, given f in sheaves on x étale, f lower star of this capital F applied to some étale morphism u to y is what?
F applied to the pullback.
Yeah, so it's F applied to u cross x over y. Great. So that was the definition. So this is now a functor. It's so the reminder is that this is a left exact functor. Which means it has right derived functors. So we get Ri f lower star now, which are functors from sheaves of abelian groups on x étale to sheaves of abelian groups on y étale. Okay, so let's study these. Let's study these functors. So here, what you're supposed to think is let me draw the Ravi person thinking. So approximately, you're supposed to think these things are taking cohomology of the fibers. Okay, and the warning is that this is not quite true. So what they are is they're, yeah, sorry, I missed Freddie had also answered the question of the definition of push forward. So The obstruction to this being true, so the obstruction to these things computing the cohomology of the fibers, is called the base change property. And we'll see later in the course that sometimes that's true. So sometimes the formation of these functors computes with base change, which means that they literally compute the cohomology of the fibers. What's true in general, and I'll discuss this later, is that if you have you can define a presheaf as follows. So what they really are, so what Ri f lower star of f does is it's the sheafification of the presheaf that sends V to Hi of f inverse of V with coefficients in f. Okay. And in general, this is not quite computing the cohomology of the fibers because this sheafification operation is a little brutal. All right, are there any questions about this? So far we have computed literally 0 examples, except for the case where y is a point. So let's talk about it a little bit. So proposition, I claim that if f is a finite morphism, then, so for example, a closed immersion, then Ri f lower star is just the 0 functor for I bigger than 0. So can anyone tell me why this is true? So what do you have to check that the derived functors of a left exact functor are what's it called? A 0.
Right exactness.
Yeah, so you have the claim you have to check is that f star is right exact. And I mean, that's the same as being exact because we know that it's left exact. And okay, so can anyone tell me how would you approach this claim? So how do you check exactness of a short exact sequence of sheaves?
You do it on the stocks.
Yeah. So the idea is to check on stocks. Okay, and I'll leave this as an exercise to you. So the point, and this is not totally trivial, but it's not too hard, is to explicitly compute the stocks of this push forward along a finite morphism. And what you'll find is that the stocks are just so let me just, right, so here the stocks of f lower star of f, or maybe I'll write the stock of f lower star of f at a point x bar in y, maybe we'll call it y bar, and y is just the direct sum over x bar in f inverse of y bar of the stocks of f at the x bars. And this is for f a finite morphism.
So we don't need f to be unramified here?
No, that's correct. So you should check this. This is not a totally trivial exercise, but it's not too hard. And so this is maybe let me write this as a must-do exercise. So maybe someone who's registered for the course can volunteer to present the solution to this exercise in a future class. Okay, cool. So we've now computed the derived push forwards, well, subject to this exercise, for finite morphisms. So let's try to understand how to analyze them in general. So first of all, I need the following technical proposition. So f star, for now any morphism f, preserves injectives. and following my rule of doing a limited amount of category theory, I'll just tell you what the key category theory that goes into this is. So this is true for any functor with an exact left adjoint. And in this case, we have the left adjoint f upper star, which we've said as a adjoint. Does anyone remember why it's exact?
Because filtered colimits are exact and sheafification is exact.
Yeah, exactly right. Or another way of saying it is you could check on stalks, and the stalks of the inverse image are just the stalks of the original functor. But yeah, that argument works too. Okay, and then the formal statement here that a functor with an exact left adjoint sends injectives to injectives is also going to be an exercise. Okay, so let me state the corollary. So this is the Leray spectral sequence. So suppose I now have F from X to Y, a morphism of schemes, and G from Y to Z, another morphism of schemes. So then I claim that there's a spectral sequence which goes from Ri G lower star composed with Rj F lower star of some sheaf F, and the infinity page converges to Ri plus J G composed with F lower star of F. Okay. So there's a special case, which is kind of the most important one, where Z is spec K, where K is an algebraically closed field. And in this case, what do we get? Well, in this case, Ri G lower star is just global sections, and same with G of F lower star, or sorry, G lower star and G of F lower star are just taking global sections. So we get a special sequence, Hi of Y with, sorry, I don't think that's quite right, Hi of, yeah, sorry, that's right, with coefficients in Hj of sorry, in Rj lower F lower star of F, and this converges to Hi plus J of X with coefficients in F. So this says that if we have a scheme which maps to another scheme, we can compute its cohomology in terms of the cohomology of certain sheaves on the target scheme. Okay. Are there any questions about the statement of this? We'll see lots of examples throughout the course. All right, so the proof is, well, there's a general statement. So I'll just write spectral sequence of a composition, but I'll say a little bit more about it. Of a composition of functors. So this is in Tohoku. So the general statement is that if you have two functors between abelian categories, so that the first one sends injectives to injectives, there's a spectral sequence computing the derived functors of the composition in terms of the composition of the derived functors. I think I have enough time to say a little bit about like how to actually get your hands on this. So how do you compute this? So let's be explicit. So let's compute our F lower star of F. So how do we do this? Can anyone tell me how do you compute the right derived functors of a given functor? Let me say Ri, F lower star of F.
You mean an injective resolution first?
Yeah, so you take an injective resolution and then you take now the cohomology of F lower star of some injective resolution, where here I, f to I is an injective resolution. Okay, so now f lower star of I is this is a complex of injectives. So what we're trying to compute now, so we want to compute G lower star of F lower star of I, right? We want really H I plus J of G lower star of F lower star of I. So this is something, here I'm just using that, I'm saying this literally is our I plus J of G composed with F lower star of F. Great. So the content here is that I don't have to replace this F lower star I with another injective resolution. Okay, and now in order to do that, you take the spectral sequence of the filtered complex. Where the underlying complex is F lower star of I bullet, and the filtration is given by the truncations. Sorry. So have you seen this notation where you take the truncation of a complex? So this is a complex whose cohomology is the same as the original one in degree up to p and 0 above p. And all you do is you take the first p minus 1 terms of your complex, then you replace the pth term with the kernel of the differential and replace it with 0 everywhere else. Okay, so this is a filtered complex. And whenever you have a filtered complex, you get a spectral sequence, and you should check that the spectral sequence has the right terms. Great. So let me just kind of maybe be explicit about one of the differentials. So here's an example of a differential. Well, you can take tau less than or equal to p of f bullet I. This maps to tau less than or equal to p plus 1 of f bullet of f star I bullet. And this maps to h, I guess, p plus 1, I think, of f I bullet in some degree. Okay, so now if you apply the derived functors of G lower star to this, you get a Long-Zat sequence, which has some maps, and then at some point you get a RQ of G lower star applied to this. What is this? This is RP plus 1 of F lower star of some sheaf F. So you get a map like this. So you get a map RP plus 1 F lower star. Sorry, I've screwed up the indices a little bit. And then via some differential to RQ plus 1 G lower star of tau less than or equal to P of F lower star of I. Okay, and this will give you, once you do a little bit of splicing, this is going to be the differential, the first differential on the E2 page of the spectral sequence. So at least in principle, like if you actually could write down an acyclic resolution or a injective resolution, these things would be reasonably concrete. You really can write down the differentials. And in real life, you kind of can't. All right, I'm out of time now. So let me stop recording, but I'll stick around for a few minutes if anyone has a question. And next time we'll talk about the Brouwer group.